And yes, we're back. And yep, in this episode, we're going to talk about recursion. And yes, if you're a computer science student or a math student, you definitely heard of recursion, and that's why you're here. But most of the time, when you just first touch recursion, it's not easy to understand. Like me, myself, when I first touched recursion as well, it's hard for me to understand how it works. So it did took me a long time in order to understand how recursion works. So that's why I made this video. So I hope this video can act as a catalyst in order to help you to understand recursion easier and faster. So in this case, this video will be chopped up into these parts. And let's go through of them. So the first thing first is take a look at the definitions. In this case, I have my sticky notes over here. In this case, yep, I did look that up on Wikipedia. And on Wikipedia, it says that recursion occurs when the definition of a concept or process depends on a simpler or previous version of itself. Like, when I first look at this, like, to be honest, like, bruh, I don't understand this. So after a couple of years into like programming and take a look into more examples, I ended up with my own definitions, which I'm going to read right now. So instead of just saying like, depends on a simpler or previous version of itself, like that does not make sense to me. The way I would say it is a function is recursive if, one, it makes a copy of itself, or it's defined by using itself. So that is recursion. So in this case, we can definitely take a look at an example. Like, we don't go immediately into the more technical examples. Just use an example that almost everyone can relate.
So here's an example, like let's say we're in a classroom and then we have 5 friends. Ukon, Mami Hinata, Chimako, Rusk, and VRChat. All of them sitting on the line, left and right, whatsoever, right? And then this is pretty much relatable. So in this case, let's just say Ukon forgot to bring her pencil, and then so she decided to ask the one on the right, which is Mami Hinata. So Mami Hinata receives the request. He also don't have a pencil. So he will ask the person on the other side, which in this case, Chimako. Now Chimako will receive this request, but Chimako don't have a pencil. So he will also ask the friend on the other side, which is Rusk. Now, in this case, Rusk also do not have an extra pencil. So in this case, she'll ask another friend on the other side, which is VRChat. And apparently, turns out VRChat has an extra pencil, or maybe he's not using the pencil at the moment. So yeah, he's chill, he's fine. So in this case, he passes the pencil back up to Rusk. Rusk get the pencil, pass it back to Chimako. Chimako gets the pencil, passes it to Mami Hinata. Mami Hinata gets the pencil, passes to Ukon, and yeah, Ukon can finally write some stuff. So in this case, the recursive function can be thought of as the function asking for a pencil and then taking the person who is asking for the pencil as an input. This can be treated as a function. If I have a pencil, all right, just give them the pencil, and if I'm agree, no whatsoever. Else, if I am the last person and I do not have the pencil, just say, oh boy, I don't have a pencil as well, sorry. Or otherwise, if I am not the last person and I do not have the pencil, I can ask the one on the other side, hey, do you have a pencil? I'm waiting for your reply. So in this case, this can be thought of as recursive as well. Now, another example is to look up the meaning of a word. It can be on the dictionary or online Wikipedia, whatsoever. So when you look up the meaning of the word, most of the time the word is described or defined by using any other words. If you find some other words that you do not understand, you have to apply the same thing again. Look it up, that word. And if that word is defined or explained by using some other words that you don't know, look up the word again, and then it just goes downwards until you hit some words such that you fully understand this word, because it is explained or defined by using all the words that you understand. Then you know the meaning of this word. So we can actually mark this word as understood. And then we can go back up a few layers, hunt for the next word that you do not understand, and then go down the layer like that. And then eventually, hopefully enough, you will search all the words you need, you will search all the meanings you need, and eventually you will figure it out, the meaning of the starting word that you want to look for. So yeah.
Okay, so now we've gone through that example. Let's see how will it work in maths. So in this case, let's just alright, probably you have seen a lot of examples. One of the example is Fibonacci sequence. That is a little bit too common. So in this case, I'm going to provide a new example. So let's come up with a recursive function. So in this case, I'm just going to define a function f of x is f of x minus 1, and then let's just go with plus 2x and then plus 5. Okay, so assume that we have this thing. Just in case, I'm writing this for myself. So in the video editing, of course, I will do animations for you out there. So in this case, so now we have this recursive function. So as you can see, this function f of x is using itself again, f inside itself. So this thing is recursive. All right, let's go straight ahead and then ask ourselves, what is f of 4? So we know f of 4 is f of 3 plus 2 times 3, that's 6, and then plus 5. Oh, okay, cool. Now we're going to ask ourselves, what is f3? So let's take a look. f3, in this case, it is f2 and then plus 3 times, 4 times 2, that's 8. Okay, I got that first one wrong. So f of 4 is f of 3 plus 8 plus 5. The second row, which is we are asking for f of 3, is f of 3 is f of 2 plus 2 times 3, that's 6, and then plus another 5. All right, and then now we're going to ask, what is f of 2? So f of 2 is f of 1, and then plus times 2, that's 4, plus 5. And then now we're going to ask ourselves, what is f of 1? So f of 1 is f of 0, and then plus 1 times 2, that's 2, and then plus another 5. Now we're going to ask ourselves, what is f of 0? So f of 0, in this case, it would be f of negative 1 plus 2 times 0, that's 0, plus 5. Alright, now we're going to ask again, what is f of negative 1? So f of negative 1 is f of negative 2 plus 2 times negative 1 is negative 2, and then plus 5. Alright, now we ended up with f negative 2. So what's f negative 2 is? Okay, just one more. F negative 32 is f negative 33, and then what else? Oh my god. Plus 2 times that, negative 64, plus 5. Okay, negative 33, f negative 33 is f negative 34 plus negative 66 plus 5. Oh lord. So yes, as you can see, we need a base case, because as you can see, if a function do not have a base case, it will keep on replicating itself, and then you'll be just like me, like calculating non-stop, and you will never get a result. In terms of math, yeah, fine, we can look at the pattern, and eventually we all know it goes to negative infinity or whatsoever, but it cannot still give you a definite answer. In computer science though, whenever you call a function, it will use up some part of your resources, and then eventually if you call way too many functions, you run out of space, and this is also known as stack overflow. So in order to fix this, let's just give our function a base case. So in this case, we only know that f of x is x minus 1 plus 2x plus 5, but as you can see, this x of f of x minus 1 will just keeps on replicating down the hall non-stop whatsoever, so we have to stop somewhere else. So in this case, let's just explicitly say when x is 0, or it means f of 0, I'm going to concretely let it be 0. So it will, so when the input is 0, it will stop replicating and then end right there. So in this case, back at our question, f of 4, right? So f of 4 will be f of 3 plus 8 plus 5. F of 3 is f of 2 plus 6 plus 5, and then f of 2 is f of 1 plus 4 plus 5, and then we have let's see, f of 1 is f of 0 plus 2 plus 5. So as we can see right here, we have f of 0 right now. So what is f of 0? F of 0 is 0. So now we know f of 1 is 0 plus 2 plus 5. So that is 7. Great. So now we know f of 1. Alright, so we back up over here. Alright, what is f of 1? F of 1 is 7. So f of 2 is 7 plus 4 plus 5. That should be 16. Okay, good. So f of 2 is 16. What is f of 3? So f of 3 is f of 2 plus 6 plus 5. Alright, which is, okay, f of 2 over here, we know it's 16. So that should be 27. Yep. And then since we know f of 3 is 27, then we know f of 4 is 27 plus 8 plus 5, which is 40. So there we go, f of 4, 40. Yay! So we have this. This is one of the examples. Now let's have another example. In this case, I'm not going to do the calculations on the screen. However, I can animate it. And so there's a small exercise. Assume that, okay, we already know Fibonacci sequence. You take the first 2 previous numbers and you add them in order to get the next number. What if in this case, the Fibonacci sequence, let's just tweak this thing a little bit. Instead of 2 terms adding together, what about 3? So in this case, the original Fibonacci sequence we know is f of x is f minus 1 plus x minus 2. So in this case, we have Fibonacci sequence, which is f of x is f of x minus 1 plus f of x minus 2. And also, very important, the base case, f of 0, let's say it's 0, f of 1 is 1 in this case. So this is the classic Fibonacci sequence. However, let's tweak things up a little bit. What we have if, okay, so in the recursive part, we have f of x plus 1, no, f of x minus 1 plus f of x minus 2 and plus f of x minus 3. So this also means that we're going to need another base case, which is f of 2 equals, let's say, it's 2. Okay? So in this case, so maybe I can start asking you, what is f of 5? So in this case, I'm not going to do the calculations over here, but in this case, you can give it a go, grab a piece of paper, try to calculate it, and when you think you're ready, I can show you the answer on the screen, animated. Play the elevator music, let's go! But of course, you can also pause the video and work on it. And then when you're ready, I'm going to animate the answer on the screen. Alright, you ready? So, here is the answer, animated on the screen. In this case, yeah. Let's see. You can actually slow down the video, just in case if you didn't catch up. Oh boy, I was a little bit laggy. Alright. But yeah. Okay, there we go. So, you get the answer. I hope that helps. Now, yeah. How did it end up there? I don't know, but yeah. So, just in case, that is recursion in maths. Well, of course, there are still way many examples out there. So, yeah. So, in this case, you can move on to the next section. Okay, so in this case, let's take a look at how recursion can be used in computer science. In computer science, there's this like one thing called depth first search. It is used to find stuff in a network by using the recursive behavior in this case. So the way that it exactly works is, the main idea is you start at some node or some starting location, and then you ask, okay, is it the thing that you want is in that node? If no, okay, look around you. Do you have any unvisited neighbors? And if yes, alright, compile them into a list whatsoever. Alright, and then go down the list. For every unvisited neighbor, you call the same function again. and then you ask them, hey, do you have any unvisited neighbors, or do you have the thing that we need? And then it goes on again and again and again until it hits the base case saying, all right, it's a dead end over here, so we're done, we're back up. Or another base case is if that location has the thing that you want in this case. So that is depth first search. So in this case, I just think, all right, it would be helpful if we have a example right here in this map. So way beforehand, I have hidden the cheese in one of the rooms over here. As you can see, by default, the cheese should be on that plate, but it's not there. So we're going to find it by using depth first search.
So just in case, before like rushing around all the places on the map over here, I have labeled all the rooms we have. In case if you need it, you can take a screenshot or write it down on a piece of paper or whatsoever. So yeah, but in this case, I hope the animation just makes it easier. So let's go. So in this case, let's start with, let's say we're starting at the center node. All right, so let's take a look. The center node has no cheese. The center node has a lot of unvisited neighbors. And so we're also going to say, all right, the center node is visited. Okay, cool. Let's take a look at it. First, we can go to the living area. Okay, and the living area has no cheese. And the living area has a lot of unvisited neighbors. And then we're going to say, okay, the living area is visited. All right, let's go to the sitting area. The sitting area has no cheese, and also it has a lot of unvisited neighbors. And we are also going to mark the sitting area as visited. Okay, let's go take a look at bathroom 2. Bathroom 2 has no cheese. Bathroom 2 at this point is a dead end, but we're still going to say, alright, we have visited bathroom 2. Now we're going back to the sitting area. Alright, next thing, let's go to bedroom 1. Bedroom 1 also don't have any cheese and do not have any unvisited neighbors. Bedroom 1 is visited as well, and then we're going back to the sitting area. Alright, let's go take a look at bedroom 2. Bedroom 2 also don't have any cheese, and then it don't have any unvisited neighbors, so at this point it's a dead end. Alright, and then we're going to say, alright, bedroom 2 is also visited, added to the visited list whatsoever. Okay, back to the sitting area. Alright, let's go take a look at the bedroom 3. Let's go take a look at bedroom 3. Bedroom 3 do not have any cheese. Bedroom 3 have no unvisited neighbors. And then bedroom 3 is visited. We're just gonna mark it. Alright, going back to sitting area. So at this point we can see, alright, sitting area has no sign of cheese. Alright, let's back off to living area. Alright, what's on the list? Alright, the flower room, or in this case the greenhouse. So let's go take a look at that. At this point the greenhouse do not have cheese. The greenhouse has some unvisited neighbors. And we also going to mark the greenhouse as visited. So let's take a look. Let's go to the study. The study has no cheese, but the study has a lot of unvisited neighbors. Alright, and then we're going to say, alright, we have visited the study. Let's go take a look. We can go to the art room. The art room has no cheese, and the art room is a dead end. So we're going to say, alright, we have visited the art room. Now we're back to the study area. Alright, next is the music room. The music room also don't have any cheese as well. music room is a dead end, no unvisited neighbors, all that stuff. Okay, music room is now visited. We're just gonna mark it. Next is the math room. The math room don't have any cheese, and the math room has no unvisited neighbors, and we're going to mark the math room as visited. Alright, let's go back to the study. Next is the natural science room. The natural science room don't have any cheese, and it has no unvisited neighbors or locations, and we're going to say, alright, we have visited the natural science room, and then we're back to the study room. The next thing on the list is the computer science room. Computer science room has no cheese and has no unvisited neighbors. And then we're also going to say, alright, we have visited the computer science room. Alright, let's go back to the study. So at this point, we can also see the study also has no sign of cheese. Alright, fine. Let's get back to the greenhouse. Alright, what's on the next thing? Dining area and kitchen. Let's go take a look. But as you can see, no cheese. Any unvisited neighbors? Yes. Alright. Dining area is visited. Alright, let's take a look at this. Okay, the next thing is platform 3. Let's go take a look at that. Platform 3 has no cheese, but platform 3 has unvisited neighbors. Alright, and we're going to mark platform 3 as visited. Alright, let's go take a look at bathroom 1. Bathroom 1 has no cheese, and it's a dead end, and we have visited bathroom 1, so yeah. Back to platform 3. Alright, the next thing is platform 4. Platform 4 has no cheese, but we have unvisited neighbors. Alright, platform 4 is now visited. There we go, on the list. The next thing, let's take a look. Okay, we can go take a look at game tent 0. Game tent 0 has no cheese, and it's also a dead end. Game tent 0 is visited. Let's add that to the list. Alright, let's go back to platform 4. Alright, let's take a look at game tent 1. Game tent 1 do not have any cheese, and it's also a dead end. And then we are going to mark, alright, we have visited game tent 1. So we're going back to platform 4. Now at this point we can see, alright, platform 4 has no sign of cheese, so let's go back to platform 3. Platform 3 at this point also has no sign of cheese as well, so let's go back to the dining and kitchen area. And then dining and kitchen area also do not have a sign of cheese, so let's go back to the living area. And then we can see living area has no sign of cheese, so let's go back to the center node. And then over here we can see, alright, we've been to the greenhouse, so we don't care, we skip it. We've been to the dining area, also no sign of cheese whatsoever, don't care, skip it. Next is the stadium. And we don't find any cheese right there, and it has no connected locations at this point. So we're going to also mark the stadium as visited. Alright, back to the center node. At this point, we can take a look at the empty platform. The empty platform is obvious enough. Empty, has no cheese as well, but it has unvisited neighbors. So also we're going to mark it as visited. Alright, let's take a look. So in this case, we can go take a look at the bench area. The bench area also don't have any cheese, but it has one unvisited neighbor. So we're also going to mark the bench area as visited. In this case, let's go to the tent, or the hemisphere tent. The hemisphere tent has no cheese, and it has no unvisited neighbors, so at this point it's a dead end. Alright, we're going to mark the hemisphere tent as visited. Alright, so the next thing Yep, so in this case, the bench area has no sign of cheese. And now, let's back off to the empty platform. At this point, we can see the hemisphere tent is visited, so we don't care, we can skip that. At this point, we can see the empty platform has no sign of cheese, so we're back to the center node. Alright, next thing we can go to is platform 1. Platform 1 has no cheese, but we have unvisited neighbors. And we can also mark platform 1 as visited. Alright, let's go take a look at platform 2. Platform 2 doesn't have any cheese, but we have unvisited neighbors. So we can also mark platform 2 as unvisited. Let's go take a look at platform 270. Platform 270 don't have any cheese as well, but it has 2 unvisited neighbors. And we can also mark platform 270 as visited as well. Alright, let's go take a look at platform 330. Platform 330 has no sign of cheese as well, but can go take a look at the unvisited neighbors because it has 1. And we can also mark platform 330 as visited. Let's go take a look at platform 330. Platform 330 has no cheese, but it has unvisited neighbors. So we can also mark platform 30 as visited. Alright, let's go take a look at platform 90. And finally, platform 90 has the cheese. So we will record the path. In this case, we're just gonna say, alright, from somewhere else, go to platform 90. That is where you can get the cheese. Alright, also we're going to say, alright, platform 90 is visited. Alright, very good. So at this point, we can say, alright, platform 30 has the sign of cheese. We're going to record the path and then back off to platform 330. At this point, we can also see platform 30 also has a sign of cheese as well. So we can record the path and then going back to platform 270. Now at this point, we can see it's a little bit redundant, but according to the algorithm, let's just run it. So in this case, let's go take a look at platform 210. In this case, platform 210 has no cheese, but it has unvisited neighbors. And then we'll also mark platform 210 or 210 as visited. So we're gonna go take a look at platform 150. Platform 150 has no cheese and it's a dead end, and platform 150 is now visited. So back to platform 210, and platform 210 has no sign of cheese. Alright, going back to platform 270. So at this point we can see, alright, platform 270 has sign of cheese. So we will record that path. In this case, we can get back to platform 2. Platform 2 has sign of cheese, record the path and all that stuff. Going back to platform 1. Platform 1 also has sign of cheese right now. Record the path, going back to center node. And then finally, center node is the starting point, and then we have the entire path from the center node to the place where we found the cheese, which is platform 90. And there we have it.
So yeah, we managed to find the cheese by using recursion. In this case, depth first search. So in this case, for those who want to look more into depth first search, I have created a function and a class in C++. It might be wrong, it might be correct, but the pseudo code is up there. And then, yep, you can definitely look more into it as well. So in this case, recursion can also be used in arts in this case. Like, obvious enough, recursion is beautiful to see and it's mesmerizing. So in this case, let's just take a look at a few examples. The first thing is very obvious enough, is the Sierpinski triangle. As you can see, we just start with a triangle and then we call out the middle of it into a triangular shape, and then now we ended up with 3 smaller triangles. Now, for every smaller triangle, do the same thing. Call out with a call out with a hole, call out with a hole, cut it out with a hole, and then each of them, they will have their own smaller triangles and keeps on going. In this case, obviously we can set up a base case and then just stop somewhere else, but the ideal Sierpinski triangle do not have a base case. So if you were to like implement this on a hardware, you're going to have stack overflow. And then if you were to like drew this on a canvas, those triangles will soon be too small such that your pencils or brushes cannot access them in this case. Now another similar shape is oh boy, is the sponge, which basically you start with a square and then you poke a hole in the middle of the square such that this whole square can be divided into a 3x3 grid, and then you just like poke a hole in the middle one. Now you will left with 8 remaining squares. Do the same thing to them recursively, and you end up with a sponge in this case. I cannot remember exactly the full name of it, but I'll definitely put it there in video editing whatsoever. So yeah. Another example is in VRChat or in Unity whatsoever. When you have a camera and then you have a render texture, and then you let the camera look at the render texture, you can see this recursive pattern. Like you can see a frame inside a frame, inside a frame, inside a frame, inside a frame, until you hit the base case, which is just rendering a single pixel. It looks like recursion, the structure is recursive, but just in case, take note over here, not exactly recursion is recursion. Sometimes some recursions are actually iterations instead of recursive. So yeah, but the structure looks recursive enough, so I'm adding that over here. And you can actually have fun with just the camera and the render textures, and then you can just play it all day. Like I remember like one of my friends, Garloid, and me just like playing with that recursion fractal thingy all day long. It was good. So yeah. So a quick wrap up. Yeah, just a quick wrap up, just to like, you know, revision what we have learned today. So recursion, quickly going through the definitions. A function is recursive if it's reusing itself in its own definition, or it makes a copy of itself. And of course it needs a base case, otherwise it will keep on replicating and then you'll end up with stack overflow. So basically this is it. If you're watching this to the very end, thanks for watching, and I'll see you in the next episode. Bye bye.